Rewiring a facility made of brick with concrete walls, especially with limited crawl space, presents significant challenges for electricians. The presence of concrete walls means they are thicker and harder than drywall or wood walls, making it difficult to drill holes for fishing cables through them. Secondly, the limited 8-inch crawl space above the ceiling is insufficient for electricians to comfortably work and maneuver, which can hinder cable pulling efforts. Thirdly, the existing conduits may already be congested with existing cables, making it challenging to insert new cables without damaging the existing wiring. Fourthly, conduits may have tight bends or obstructions that can make it difficult to push cables through them. To address these challenges, electricians may need to employ various techniques. One technique is using snakes or fish tapes to guide the new cables through the conduits. However, this method can be time-consuming and difficult in tight spaces. Another technique is wall chasing. If the conduits are inaccessible, electricians may need to chase the walls and ceilings to create new pathways for the cables. This involves cutting into the concrete walls and ceilings, which is a more labor-intensive and time-consuming process. Another point to consider is the removal of existing cables. In some cases, it may be necessary to remove existing cables from the conduits to make room for the new cables. This requires disconnecting the cables from the panel boards and receptacles, which can be a significant task. Given these challenges, it's reasonable to estimate that the electrical work may require extensive wall and ceiling demolition to facilitate cable pulling. This would increase the labor costs and timeline for the project. It is advisable to explore alternative solutions to avoid the need for extensive demolition. Alternative solutions could be installing surface-mounted conduits, which involves running the new wiring along the surface of the walls and ceilings within a protective conduit. This approach minimizes the need to penetrate the concrete structure and can be a less disruptive option. Another potential solution involves wireless power distribution systems. These systems transmit power wirelessly to designated points, eliminating the need for extensive wiring. While they may not be suitable for all applications, they could be considered for powering specific devices or areas within the facility. When planning a project involving electrical work in concrete structures with limited access, it's important to carefully assess the existing conditions, consider the potential challenges, and explore alternative solutions to minimize disruption and control costs. The National Electrical Code, or NEC, provides guidelines and standards for electrical installations, including requirements for conductor sizing, overcurrent protection, and wiring methods. Article 300.11 of the NEC addresses securing and supporting wiring. It states that wiring must be securely fastened in place. This ensures that the wiring is not subject to undue stress or movement, which could damage the insulation or connections. The type of support used will depend on the type of wiring and the installation environment. Common supports include cable ties, straps, and clamps. Article 310.15 of the NEC covers ampacity of conductors. Ampacity refers to the maximum current, measured in amps, that a conductor can carry continuously under specified conditions without exceeding its temperature rating. This section provides tables and guidelines for determining the appropriate conductor size based on the load requirements, ambient temperature, and other factors. Using the correct conductor size is crucial for preventing overheating, insulation damage, and potential fire hazards. Article 314 of the NEC deals with outlet, device, pull, and junction boxes, conduit bodies, fittings, and handhole enclosures. These enclosures are used to protect electrical connections and provide access for maintenance and modifications. The NEC specifies the minimum size and type of enclosure required based on the number and size of conductors, as well as the environment in which the enclosure is installed. Proper selection and installation of enclosures are essential for ensuring the safety and reliability of the electrical system. Article 330 of the NEC addresses metal-clad cable, also known as MC cable. MC cable is a type of cable that consists of insulated conductors enclosed in a metallic sheath. It is commonly used in both exposed and concealed wiring applications. The NEC specifies the allowable uses, installation requirements, and ampacity ratings for MC cable. This includes guidelines for supporting the cable, making connections, and protecting it from physical damage. Article 344 of the NEC covers rigid metal conduit, or RMC. RMC is a type of raceway made of heavy wall steel or aluminum tubing. It is used to protect and route electrical conductors in various environments, including those subject to physical damage or corrosive conditions. The NEC specifies the allowable uses, installation requirements, and support intervals for RMC. This includes guidelines for cutting, threading, and bending the conduit, as well as for making watertight connections. Article 348 of the NEC addresses intermediate metal conduit, or IMC. IMC is similar to RMC but has a thinner wall thickness, making it lighter and easier to work with. It is commonly used in both exposed and concealed wiring applications. The NEC specifies the allowable uses, installation requirements, and support intervals for IMC. This includes guidelines for cutting, threading, and bending the conduit, as well as for making watertight connections. Article 350 of the NEC covers flexible metal conduit, or FMC. FMC is a type of raceway that consists of a flexible metal tube. It is used to protect and route electrical conductors in locations where flexibility is required, such as for connecting to motors or other moving equipment. The NEC specifies the allowable uses, installation requirements, and support intervals for FMC. This includes guidelines for cutting and connecting the conduit, as well as for ensuring that it is properly grounded. Article 352 of the NEC addresses rigid polyvinyl chloride conduit, or PVC conduit. PVC conduit is a type of raceway made of rigid plastic tubing. It is used to protect and route electrical conductors in corrosive environments or when non-metallic materials are required. The NEC specifies the allowable uses, installation requirements, and support intervals for PVC conduit. This includes guidelines for cutting, bending, and joining the conduit, as well as for ensuring that it is properly supported. Article 356 of the NEC covers liquid-tight flexible metal conduit, or LFMC. LFMC is a type of raceway that consists of a flexible metal tube with a liquid-tight outer jacket. It is used to protect and route electrical conductors in wet or damp locations. The NEC specifies the allowable uses, installation requirements, and support intervals for LFMC. This includes guidelines for cutting and connecting the conduit, as well as for ensuring that it is properly grounded and sealed. Article 358 of the NEC addresses electrical metallic tubing, or EMT. EMT is a type of raceway made of thin wall steel or aluminum tubing. It is commonly used in concealed wiring applications. The NEC specifies the allowable uses, installation requirements, and support intervals for EMT. This includes guidelines for cutting, bending, and joining the tubing, as well as for ensuring that it is properly grounded. When pulling new conductors through existing conduits, several factors can affect the difficulty of the task. These factors include the conduit size, the number and size of existing conductors, the presence of bends and offsets, and the condition of the conduit and conductors. If the conduit is undersized or already crowded with conductors, it may be difficult to pull additional conductors without damaging the insulation or the existing wiring. Similarly, if the conduit has numerous bends or offsets, the pulling force required may be excessive, increasing the risk of damage. The condition of the conduit and conductors can also play a role. If the conduit is corroded or damaged, it may have sharp edges or obstructions that can snag the conductors. If the existing conductors are old or brittle, they may be more susceptible to damage during the pulling process. To minimize the risk of damage when pulling conductors, it is important to use proper techniques and tools. These include using a pulling lubricant to reduce friction, using a pulling eye or basket grip to distribute the pulling force evenly, and using a fish tape or pulling rope to guide the conductors through the conduit. It is also important to avoid exceeding the maximum pulling force recommended by the conductor manufacturer. If the pulling force becomes excessive, it may be necessary to use a larger conduit or to install a pull box to reduce the length of the pull. When working with electrical systems, it is essential to follow safe work practices to prevent electrical shock and other hazards. These practices include energizing the circuit before working on it, using appropriate personal protective equipment such as gloves and eye protection, and verifying that the circuit is energized using a voltage tester. It is also important to be aware of the potential hazards associated with working in confined spaces or near energized equipment. If you are not qualified to perform electrical work, it is best to hire a licensed electrician to do the job. Electrical work can be dangerous, and it is important to take the necessary precautions to protect yourself and others from harm. Electrical panels have circuit breakers which protect electrical circuits from overloads and short circuits. When a circuit breaker trips, it interrupts the flow of electricity to the affected circuit, preventing damage to the wiring and equipment. It's generally best to use a copper conductor for electrical wiring due to its superior conductivity, durability, and safety characteristics. Copper has a higher conductivity compared to aluminum, allowing it to carry more current for a given size. This reduces the risk of overheating and voltage drop, which can affect the performance of electrical equipment. Copper is also more resistant to corrosion than aluminum, making it a more durable option for electrical wiring. Copper connections are also more reliable than aluminum connections, reducing the risk of loose connections and electrical fires. In residential wiring, 14 American wire gauge, or AUG, and 12 AWG copper conductors are commonly used for lighting circuits and receptacle circuits. For larger appliances and equipment such as air conditioners and electric ranges, 10 AUG, 8 AWG, or larger conductors may be required, depending on the amperage rating of the appliance. In commercial and industrial wiring, larger conductors such as 6 AWG, 4 AWG, 2 AUG, or larger are often used to supply power to lighting, receptacles, and equipment. The size of the conductor required will depend on the load requirements and the length of the circuit. When installing electrical wiring, it is important to follow the NEC guidelines for conductor sizing, overcurrent protection, and wiring methods. This will ensure that the electrical system is safe, reliable, and compliant with applicable codes and standards. In the scenario described, add a new 400 amp and 225 amp 3-phase 208/120 volt panel boards is a significant undertaking that requires careful planning and execution. It's important to consider the available space for the new panel boards, the load requirements of the circuits that will be fed from the new panel boards, and the existing electrical infrastructure. The new panel boards must be properly sized to accommodate the anticipated load and must be installed in accordance with the NEC and local electrical codes. The feeders supplying the new panel boards must be sized appropriately to handle the total load of the panel boards, taking into account demand factors and other relevant considerations. Overcurrent protection must be provided for the feeders and branch circuits to protect against overloads and short circuits. The new panel boards must be properly grounded to ensure the safety of personnel and equipment. The grounding system must comply with the requirements of the NEC and local electrical codes. The electrical work must be performed by qualified electricians who are familiar with the NEC and local electrical codes. They must follow safe work practices to prevent electrical shock and other hazards. Once the new panel boards are installed and wired, they must be inspected and tested to ensure that they are functioning properly and that they comply with all applicable codes and standards. A licensed electrical inspector must perform the inspection. The NEC provides detailed requirements for electrical installations, including those involving new panel boards and feeders. Some of the key articles that are relevant to this type of project include Article 220, which covers branch circuit, feeder, and service calculations. This article provides guidelines for calculating the load requirements of electrical systems, including lighting, receptacles, and equipment. Article 230 covers services. This article addresses the requirements for electrical services, including the size and type of service conductors, overcurrent protection, and grounding. Article 240 covers overcurrent protection. This article specifies the requirements for overcurrent protection devices, such as circuit breakers and fuses. Article 250 covers grounding and bonding. This article outlines the requirements for grounding and bonding electrical systems to ensure safety and prevent electrical shock. Article 310 covers conductors for general wiring. This article provides information on conductor sizing, ampacity, and installation requirements. Article 408 covers switchboards and panel boards. This article specifies the requirements for switchboards and panel boards, including their construction, installation, and wiring. When planning and executing an electrical project involving new panel boards and feeders, it's important to consult the NEC and local electrical codes to ensure that the installation complies with all applicable requirements. This will help to ensure the safety and reliability of the electrical system.